If I were to ask you, what's the most expensive part of a rocket? Many might guess it's advanced technology systems, the materials used for its construction, or even the cost of the fuel. However, the real answer lies within its engines. These engines are not just any part of the rocket, they are the crucial components that provide the thrust needed for liftoff. This is especially true for rockets like Starship, which is the world's largest spacecraft. During its recent third flight, the rocket achieved 80% of its mission objectives successfully as planned. In this video, we'll dive into whether the remaining 20% of the mission's challenges were related to the engines or if there were other factors. Before we delve any deeper, make sure to subscribe to our channel for future updates about the Starship and SpaceX's other groundbreaking achievements. SpaceX has always focused on developing its own rocket engines instead of using ones already available on the market. This approach started with the creation of the Merlin engines, which are used on the Falcon rockets. These engines are powered by RP-1, a type of kerosene, and liquid oxygen. The Merlin engine is known for its high thrust-to-weight ratio, making it very efficient for its size. It has been a critical component in achieving the reusability of the Falcon 9's first stage. After the Merlin engines, SpaceX developed the Kestrel engine for the Falcon 1's upper stage, and the Super Draco engines for the Dragon spacecraft. The next significant development was the Raptor engine, designed for the Starship spacecraft. The Raptor uses a full-flow staged combustion cycle, a first for an operational engine, which allows for more efficient fuel use. It runs on methane and liquid oxygen, which could potentially be sourced from Mars in the future, aligning with SpaceX's goals for Mars colonization. After developing the Raptor engine, SpaceX introduced the Raptor 2, an upgraded version that offers significant improvements in terms of thrust. The Raptor 2 is now being used in SpaceX's Starship test flights. The Starship Super Heavy booster is powered by 33 Raptor engines. This massive array of engines is a testament to the power required to propel the Starship into orbit and beyond. The Starship itself uses 6 Raptor 2 engines for operation in the vacuum of space. The Raptor 2 engines boast an impressive thrust capacity, which is critical for the ambitious missions SpaceX envisions for the Starship, including crewed missions to Mars and beyond. Each Raptor 2 engine is capable of producing about 230 tons of thrust at full power. We all witnessed the impressive performance of the Super Heavy's 33 Raptor engines during the launch on March 14th. Shortly after launch, the vehicle reached Max Q, the point of maximum aerodynamic pressure, a critical phase for any rocket. The broadcast showed various angles of the rocket ascending, thanks to multiple onboard cameras. Unlike the challenges faced during the first 2 test flights, the third launch saw the engines performing without any issues, consuming around 40,000 pounds of propellant per second upon ignition. At T+2 minutes and 44 seconds, the stage separation occurred. This was executed flawlessly, with most of the booster engines shutting down except for 3, allowing for a controlled separation. Immediately after, the upper stage's 6 engines ignited, marking the start of its journey to orbit. During the first flight, the launch sequence encountered significant issues, including 3 engines failing to start or aborting before liftoff, and several others failing during the flight. This led to the vehicle not attempting stage separation, eventually tumbling and disintegrating nearly 4 minutes into the flight. The aftermath of this test resulted in the Federal Aviation Administration grounding the launch program pending a mishap investigation, which SpaceX completed by submitting corrective actions to the FAA before being allowed to conduct another launch. During the second flight test of the Starship, the spacecraft faced issues related to the stage separation process. The separation took longer than planned, and this had a significant impact on the mission's outcome, as it led to the booster being exposed to the intense heat generated by Starship's engines for a prolonged period. The exposure to the heat from the Starship's engines caused damage to the booster, ultimately resulting in its explosion. SpaceX responded by making several upgrades to the engine system, including improving the igniter and introducing an electric system for thrust vector control, replacing the hydraulic system. They also made adjustments to reduce fuel sloshing, and these upgrades paid off in the recent third flight. However, despite these improvements, challenges remained. The Raptor engines encountered issues during the landing attempt of Booster 10, with a delayed engine reactivation and only 3 engines restarting, leading to a high-speed landing and subsequent explosion of the booster. SpaceX aims to address these issues in future Raptor engine iterations, with a focus on enhancing engine reactivation stages for safer landings. The first Starship launch attempt lasted 4 minutes, and the second lasted 8, with the latter reaching space. The third lasted more than 50 minutes. In the third flight of SpaceX's Starship, the spacecraft completed its first orbital flight, but lost communication during re-entry into Earth's atmosphere. This was an expected part of the test, as SpaceX did not plan to recover the Starship for this mission. The vehicle was supposed to enter the Indian Ocean, and it's presumed that it either burned up or broke apart upon re-entry. This test was important for assessing the Starship's performance, particularly its ability to withstand the harsh conditions of atmospheric re-entry. SpaceX's ongoing issues with its Raptor engines are becoming a big concern, especially as its main competitor, Blue Origin, successfully debuted its BE-4 engine on United Launch Alliance's Vulcan Centaur rocket. To address this, SpaceX is progressing with its Raptor 3 engines for future Starship flights. The Raptor 3 achieves 350 bar of chamber pressure and 269 tons of thrust, marking an increase of 17% more thrust compared to the Raptor 2 engines. The Raptor 3 engines are designed not only to provide more thrust, but also to reduce the weight of the engines and, by extension, the entire rocket. This is achieved by removing unneeded parts and possibly reducing the rocket's weight by another 200 kilograms per engine, which, for the 40 engines used across the Starship and Super Heavy booster, translates into a significant reduction in total vehicle mass. When comparing the capabilities of the Raptor 3 with Blue Origin's BE-4, SpaceX's enhancements could offer several advantages. The Raptor 3's increase in thrust, coupled with efforts to lower the engine and vehicle mass, directly contributes to a more efficient launch system. Musk's SpaceX has set an ambitious target to launch at least 9 Starships in 2024. With 1 launch already completed, this leaves 8 more launches for the year, implying a high frequency of Starship launches. However, achieving this goal may be challenging, especially considering regulatory hurdles. The FAA may not grant approvals quickly, especially after categorizing a previous flight as a mishap, despite it completing 80% of its objectives as planned. The FAA's stringent regulations and slow processing have previously delayed SpaceX's launch plans. SpaceX has criticized these delays, attributing part of the problem to the FAA being understaffed. The company suggested that the FAA increase its licensing staff and consider prioritizing national interest projects to streamline the process. And that's all for today's update. If you enjoyed watching and found it useful, please make sure to subscribe to our channel and hit the like button. Thanks for watching, and I'll see you in the next one.